Hey there, today we'll be going over the math behind 3D graphics. Specifically, we'll be going over how we project our 3D meshes onto our 2D screens for our eyes to interpret. In our engine's code, this occurs in the vertex shader stage. If you remember correctly from our previous video, the vertex shader stage is a shader code stage, meaning that we'll have to make our own code for it. To learn the math behind projection though, we first need to go over a bit of the basics of linear algebra, as this is the primary way that we will apply transformations to our vertices. The first concept that we need to understand in linear algebra is vectors. Imagine a blank empty space with two lines that intersect perpendicular to each other. The horizontal line we will call the x-axis, and the vertical line we will call the y-axis. The point at which these two lines intersect will be called the origin. Now imagine taking an arbitrary length and dividing each axis by that length. We will call that length 1 unit. The space that we imagine will be called our xy plane. Now let's create an arbitrary vector. You will represent this vector in our Cartesian coordinates, which is a set of values that represent the offset of the tip of the vector from each axis. In this two-dimensional example, the first number represents the offset from the y-axis, a positive number representing a rightward motion, and a negative number representing a leftward motion. And the second number represents the offset from the x-axis, a positive number representing an upward motion, and a negative number representing a downward motion. Vectors are not points. This is very clear in mathematical notation, as they will be represented in square brackets, not parentheses. As a variable, vectors will be also represented with a little arrow above their name. In Cartesian coordinates, each set of unique coordinates represents a unique vector in our plane. Anyways, vector addition and multiplication. These are two concepts that nearly every topic in linear algebra will connect to. To add two vectors together, we simply take the tail of one vector and attach it to the end of the other vector. The point that the chain of vectors point to can be represented as a new vector, and this new vector is the sum of our two vectors. Notice how for this operation order does not matter. If we were to switch the vectors, we would still get the same sum. This means that vectors have the commutative property of addition. Another way you can think of this is dividing each vector into its x and y components and representing each component on its own number line. Think of our two original vectors as motion. We first move 1 unit to the right in the right direction with our first vector, and then 2 units to the right in the right direction with our second vector. We can do the same thing to the y-axis, and you can see that we get the same vector as before. Our second basic operation is vector multiplication. Let's say we multiply the vector by 2. The length of our vector gets doubled. If we were to multiply the vector by a fraction, like 1/2 for example, our vector's length would be squished and it would get smaller. A negative number would change the direction of the vector, making it go backwards. This is called scaling, and the number we multiply a vector by is called the scalar. Think of this operation like distributing a scalar to each component in our vector, similar to distributing a variable and expanding a polynomial. For the majority of you, you probably have already heard of everything I had just explained. Now, let's think of the components of our vectors as scalars. Let's imagine that there are two vectors that represent our coordinate system. The one on our x direction will be called I hat, and the one on our y direction will be called j hat, both with a length of 1. Let's look back at our original vector. Think of our first scalar as a scalar that scales I hat, and our second scalar as a scalar that scales j hat. Think of our original vector as the sum of the two scaled vectors. Together, I hat and j hat are called the basis vectors of the xy plane. And think about how if you apply transformations to these basis vectors, it would also apply transformations to our original vector. Imagine if we chose two new vectors as our basis vectors. In theory, we could still reach any value that our original I hat and j hat could reach. However, our scalars would be much different. This is pretty cool, as it means that there is an infinite amount of coordinate systems, each of which can reach an infinite amount of points. Focusing back on our original topic, anytime we scale and add vectors like this, it is called linear combination. If you leave one scalar constant and change the other, it draws a line. However, if you were to let both scalars change freely, you can generate all possible points in the plane. There are a few exceptions though. If our basis vectors were to line up on the same axis, Unfortunately, we would be locked to that one specific line, and wouldn't be able to make any points that aren't on that line. If our basis vectors both had a length of 0, we would be stuck at the origin. This range of possible values that we can reach is called the span of the linear combination. Let's go back to our previous example. Here, the span is the entire xy plane. Both the basis vectors are also considered to be linearly independent, as they both add values to the span. Here in the next example though, the span is only the x-axis, and the basis vectors are considered to be linearly dependent, as if you were to remove either of them, the span would stay the same. Now that we got those basic concepts out of the way, we can get into the meat of what is used in the vertex shader, the linear transformations. Conceptualize a transformation as a function. You give an input which gets transformed into our output. Imagine a bunch of points in our plane. Think of a transformation as a uniform movement to all of those points. There are many types of transformations, but we will limit ourselves to linear transformations, which have two rules. All straight lines must remain straight, and the origin must not move. Think of it like making sure the grid lines of our graph remain parallel and evenly spaced. Imagine our I-hat and j-hat coordinate system with a random vector. When we apply a linear transformation to I-hat and j-hat, our output of the linear combination is our transform vector. We can solve for the transform vector only knowing the original vector, our new I-hat, and our new j-hat, since the linear combination is still the same. Now, let's think about this numerically, not visually. Given an arbitrary vector AB, and our transformed I-hat and j-hat, we can use linear combination to solve for our transform vector. A times the vector I-hat plus B times the vector j-hat gives us our final vector. This means that any linear transformation in 2D can simply be represented by four numbers, the two scalars of I-hat and the two scalars of j-hat. Now, some really old dead mathematician decided to arrange these numbers together in a 2x2 grid called the 2x2 matrix. Then he found that matrix vector multiplication is the linear combination of the I-hat and j-hat from our matrix with a given vector. Remember how I was previously talking about linearly independent and dependent basis vectors? Imagine if our new I-hat and j-hat and our transformation were linearly dependent. The transformation would squish all of our 2D objects into 1D. Pretty cool, right? Now, let's move on and think of multiple linear transformations, applying one after another. This stacking of transformations is called composition. For example, imagine we had two linear transformations, a rotation and then a scaling. The long way to compute it would be to apply the transformations individually. But imagine if there was a way to compute a single transformation matrix that would apply both transformations at once. This transformation matrix is produced by simply multiplying the two transformation matrices together. For some reason, another random dead dude decided that this matrix multiplication be read from right to left, not left to right. The idea being that these transformations are functions, and in function notation, we write the function name on the left side of the function's inputs. First, let's look at these two new transformation matrices shown on your screen. This is what happens when you transform by t1, and this is what happens when you transform by t2. Now, let's look at them mathematically. First, take the I-hat vector of t1 and transform it by t2. Then set our I-hat vector in our composition matrix. Then do the same thing with the j-hat vector. This is our final composition matrix. Notice how order does matter here, as if we do the rotation first, our final vectors for I-hat and j-hat are different than if we do the shear first. So the order of the composition transformations does matter, meaning it does not have the associated property of multiplication. This stresses the importance that we need to think about matrix multiplication as transformations being applied. In different orders to transformations result in different final results. Now that we've touched a little bit on linear algebra, we can start looking at how this applies to 3D graphics. If you didn't understand some of the concepts highlighted previously, now is a good time to pause the video and rewatch it, or look for some external resources for help. When we load a mesh in Banan, it is composed of vectors from the center of our model to the position of a given vertex that makes up the surface of each model. As you know from the last video, these vertices are organized into triangles in the input assembly stage, and are later used for rasterization and coloring. For now though, we need to transform these vertices from relative to the center of the object to relative to the center of the camera in our world. Let's start by creating a 3D world. Remember, in Vulkan we use the left-handed coordinate system, so our y-axis is actually down. Our x-axis will be red, and our y-axis will be green, and our z-axis will be blue. Note how these transformations are not necessarily linear, as some of them do make translations. However, the same concepts can apply. Our brain already does the hard part of rendering. It takes a 2D image from our eyes and is able to process it and understand it as a 3D object. So all we need to do is transform the 3D triangles that make up our mesh to our 2D screen space. So we need to think of our camera as a 2D window in our world, where the window is our screen. There's two standard ways to render the world through our window. The first one you may have already heard of, ray tracing, where we basically just project a bunch of rays through our window into the scene and see what color comes back. However, this method is rather expensive, and it is only until recent advancements in hardware that real-time ray tracing became possible. However, this method is used extensively in non-real-time industries like movies, which can take hours to render a single frame. The other method is object-ordered rendering, where we draw objects individually on our window, and this is used extensively in real-time computer graphics and will be what we focus on in Banan. The first transformations we are going to apply are these two transformation matrices you see here. The first matrix is our model transformation matrix. This accounts for any transformations we would want to apply to the object relative to the world, such as character movement and object movement. The next matrix is the view matrix. This matrix accounts for the camera's rotation and position in the world. Think of this like a backwards model matrix. When we turn the camera left, we don't actually turn the camera itself, but we turn the entire world right. When we move forward, we move the entire world backwards. Some of you may notice that we have a fourth component to our 3D position vector, and that we're using 4x4 matrices. This fourth component is called the homogeneous coordinate, and we'll get back to why this is important later. The way these two matrices are derived are rather straightforward. The first thing in these that we'll account for is our rotation transformation. Rotations are very complicated in 3D compared to 2D, as in 3D we have 3 axes of rotation, while in 2D there's only one possible axis of rotation. We'll be representing rotations through Euler's angles. Euler's angles are composed of 3 values, each representing a rotation on a different axis. However, I do acknowledge the fact that Euler's angles are flawed and are rarely used over quaternions, mainly because of the issue of gimbal locking, where we lose some degree of rotational freedom in some scenarios. Since Euler's angles can be represented as 3 2D rotations, we can consider Euler's angles as 3 transformation matrices and multiply them together to get our final rotation. The question is, what order of transformations do we use? There's 2 general groupings, the first being proper Euler's angles and the second being Tate-Bryan angles. Proper Euler's angles are composed of 3 rotations, with the first and last rotation being on the same axis, but the middle bit rotation being on a different axis. Tate-Bryan angles are composed of 3 rotations, each rotation on their own axis. In reality, all these orders are completely valid, but I noticed that the majority of rendering engines use Tate-Bryan angles, and while there probably is a technical explanation for it, I find them easier to understand conceptually as you each have a unique axis for each rotation. For Banan, we use the order YXZ for a rotation matrix. Now we look into the derivation of each rotation matrix. Remember those cool identities that we learned in pre-calculus? Those are pretty useful now. Specifically, the summation angle identities. So, let's apply this to our rotation matrix. We can say that A is the current angle of rotation, and B is the angle that we are going to add on to angle A. In the formula, we can substitute x in for cosine A, and y in for sine A. Therefore, our desired vector for a 2D rotation is x cosine theta minus y sine theta, x sine theta plus y cosine theta. We can factor out the x and y vector to get this final transformation matrix for 2D rotations. Now, let's think about 3D rotations. Imagine what components change when you rotate a position around the z-axis. Here, you can see that is the x and y components, and we can imagine this as a 2D rotation while looking down the z-axis. Since a 3D rotation on the z-axis is pretty much the same as a 2D rotation with the x and y values, we can plug in our 2D rotation matrix and fill the rest of the values with the identity matrix values, since z is constant. This same concept can be applied to the other rotation axes to get these matrices. Here, theta x represents rotation on the x-axis, theta y represents rotation on the y-axis, and theta z represents rotation on the z-axis. Now, we can multiply these rotation matrices together in the order of y, x, z to get our final Tate-Bryan rotation matrix. Pretty simple, right? Now, let's try to derive our model matrix and view matrix. Since our position is a 4-component vector with homogeneous coordinate, we need to multiply by a 4x4 matrix. Our rotation should only affect the x, y, and z values, so we're going to plug it in like this. Then, we can put our translation here on the last column. Ignore the first 3 columns for a second and think about how this would multiply out with a 4-dimensional vector. It would multiply this column by the homogeneous coordinate and then add it to our first 3 coordinates. So, this acts as sort of a translation. And this is our final model matrix. Now, our view matrix is pretty much the same thing, just all the values are negatives since it's accounting for the camera's positioning, not the model's positioning. At this point, you either have a straightforward understanding of everything that's going on so far, or you're completely lost. So you have 2 options here. You can go back through the video to find where you got lost and search up something about it and learn it yourself, or we can go on to the hard part. So this is a good pausing point. Our last matrix is a little bit more complicated. Our projection matrix. The job of our projection matrix is to create the illusion of perspective. Remember, in Vulkan, positive x is to the right, positive y is downwards, and positive z is into the screen. We are going to start with a really basic projection transformation. Just a box that scales the screen to the Vulkan canonical view volume. For now, we're going to assume the screen has the same aspect ratio as this video, 16:9. Vulkan's view volume is just a cube with a length of 2 on each side. However, our computer screens are rectangular, so we need to apply a transformation that converts a rectangle into a square. This red box here is our Vulkan canonical view volume. For this projection transformation, we are going to make a composition of 2 transformations. Our box could be positioned incorrectly, so first we need to translate the box to the center of the screen. To do this, we simply need to translate to the point 0, 0. So we take the position of the center of the box by using the position of the right plane and the left plane to find the center on the x-axis, and the position of the top plane and the bottom plane to find the position on the y-axis. And then we translate by that vector. This would look like this in our 4x4 matrix. The variables r, l, b, t, and f refer to right, left, bottom, top, near, and far respectively. Now, we need to think about our second transformation, the scaling. This matrix is applied to scale our box from the standard size of 2, 2 to match the aspect ratio of the monitor. We compose these 2 transformations together to get this final transformation matrix. This matrix is called our orthographic projection matrix. Now, let's focus on real life for a second. If we project a ray from our eyes in real life, we have a depth cube called retinal image size, where if we know the size of an object, we can determine how far away it is based on the size of it in our vision. This is because in real life, things appear smaller as they get further away. However, in our box projection, this isn't true. Imagine shooting rays through our window. No matter how far or close the object is inside of our box, the same rays will be activated. However, for an object to appear bigger in real life, more rods and cones in our eyes are activated, and for an object to appear smaller in real life, less rods and cones are activated. So we need to create this shape that's similar to a pyramid called a square frustum. Think about how rays would go through this frustum. They would go through at an angle, not straight through. Imagine an object closer to the front of the frustum. It would cover more rays than an object that's farther away. So obviously this is a solution from a programming perspective. we first should transform our vertices from our view frustum to the orthographic view space, and the orthographic view space will transform the vertices to our Vulkan view space. Let's think of this from a side view. The plane in our front is our near plane, which represents the screen, and this dot on the left represents the location of our camera. We can draw a triangle with these two, and then extend the hypotenuse of the triangle to the far plane to form our view frustum. Let's imagine an object somewhere between our near plane and far plane. We know that by the angle-angle proof, the triangle that forms for our near plane to viewer object is congruent to the triangle that forms from our world object to viewer object, as all angles in both triangles are the same. Therefore, the ratio of the two legs are the same for both triangles. This can be rearranged as an equation to solve for the height of the object on our near plane, which is our screen. This same concept can be also applied to our width. So our final position of our vertices should look something like this. However, there is no transformation matrix that I know of that only applies a division of z to the first two components of the vector, but not the third. Remember, the third component depth is very important, as it determines which vertices appear on top of each other. Remember the homogeneous coordinate I was talking about earlier? This is when it comes into play. We will tell Vulkan that whenever it solves for the position of any vertice, the output of the vertex shader will be a 4-component vector. And to solve for the 3D position, we divide each component of the vector by the fourth component. This way, we consider fourth component the z, and when Vulkan tries to solve for the 3D position of a vertice given our 4D vector, it will implicitly divide the x and y components by z. Now, let's look at our transformation matrix. The issue is, if we were to just pass z through, we would get z by z, which is equal to 1, losing our depth information. If you were to multiply out the matrix, you see that there are only currently 2 remaining values that we can use to manipulate z, without manipulating the x and y of our positions. This will be represented by a and b, and since we want z to be z squared, we can make the equation az plus b is equal to z squared. This equation is quadratic, meaning at most it will have 2 real solutions to it, meaning there will be only 2 points where our z value matches the exact z value of our object. In this case, we want our 2 real solutions to be the bounds of our z buffer, as we do not want to exceed them. So one is for when z is equal to the distance of our near plane, and one is for when z is equal to the distance of our far plane. We can plug in our near and far plane distances in for z, and create a system of equations that can be used to solve for a and b. Now, here's the ideal depth distribution for objects into the near and far plane. It's a straight linear distribution. However, with our system, our z approximations look something like this. Even though it's curved and doesn't match our ideal depth distribution, as you can see, we can still use it to determine the correct ordering of our objects, as near objects still have a lower z value than farther away objects. Now, we can simply stack these transformations together to form our final projection matrix, which can be represented by this. This matrix uses 6 values: the distance of the center of the right plane, left plane, bottom plane, top plane, near plane, and far plane from the center of our screen. We can further simplify this matrix down a bit. Since the z-axis comes out of the center of the screen, we know that the scalar that represents the center of the left plane is the same as the scalar that represents the negative value of the center of the right plane. And the same thing for the top and bottom. We can use that to simplify the matrix down a little bit to this. Finally, remember, we're making a rendering engine here, and the target user here is gamers. Monkey brains, right? So they don't want to understand the math of how to increase the FOV in the game. They just want a slider that can be adjusted for them. Given our aspect ratio of the window, along with the angle of the field of view which the user would like to see, we can use some trigonometry to solve for the values of our bottom plane and right plane. And since we know the bottom plane and right plane are just negative values of the top plane and left plane, we can plug this into our matrix like this. Now this forms our final projection matrix that is used in Banan. We simply multiply the vertex position as a 4-dimensional vector by our model matrix, then our view matrix, and then our projection matrix to get our final position that we send to Vulkan. Vulkan then divides our first 3 components of the vector by the 4th component to get our screen space position and depth of the vertex. This is the 2 lines of code that make up the vertex shader of Banan. And that's about it. Cheers.